Okay, everybody, welcome to room 2 for our first contributed talk session. Our first speaker will be Atish Mitra from Montana Tech, talking about the space of persistence diagrams on endpoints, coarsely embeds into Hilbert Space. Turn it over to Atish.
Thanks, Greg. It's a pleasure to speak here once again. So this mode of delivery is not my favorite one, but what can we do? So I'll be talking about something I have been doing, have been involved in the last 1.5 years or 2 years or so. So I usually work in either cohomological dimension or coarse geometry or covering spaces. But recently, for the last 2 years or so, I have been dabbling, is the correct word probably, in a little of this applied topology. So we heard this morning from one of the experts, Peter Bottleneck, on persistent homology. So I will totally skip that part because he explained everything pretty well and set the stage. So the problem I'll be interested in is a problem he mentioned lightly, the problem of embedding spaces of persistence diagrams in Hilbert space. And he did mention what are the benefits that all sorts of statistical softwares can be used. One can calculate means and all sorts of other statistical parameters once you have this Euclidean structure. And this problem was solved using coarse geometry, which I have been doing for a few years. So that's what I will be talking about. So as I will totally skip this persistence, the applied topology part, so I will just mention a couple of words that this idea of persistence is what I think of as is sort of a meta definition, is a mathematical formalism that deals with how the shape of a data set evolves with scale. One can think of the scale as a scale around a point cloud, scale of balls around a point cloud. So for example, a simpler example than homology is Euler characteristic. Euler characteristic as increasing scales of observation. So that was what I started with looking at with a bunch of physicists about 2 years ago in 2019. And we had a bit of success on that. And then me and Jiga, my friend Jiga, started looking at these persistence diagrams. So that's the very brief history of it. So by the way, this Euler characteristic idea, we looked at it increasing scales. This persistence of it is now out. We looked at some fluid mechanical features using this idea of Euler characteristic surfaces. This is recently published by Physics of Fluids during the lockdown of last year. So my entire overview of persistence will be, persistent homology will be through this nice picture taken from a paper of Chazal and others who are experts in these sort of things. So this just gives us a reminder of what Peter told us this morning, that we have a point cloud, and if we look at increasing balls around the point clouds, we can look at features such as connected components, which are encoded by the red bars, or non-trivial loops, which are encoded by the blue bars. And then these bars are further encoded and summarized by these dots, this set of dots, which constitute the persistence diagram on the portion above the diagonal of the first quadrant. So that's the summary of persistence diagrams, which was explained this morning. So the question is, so this is a particular persistence diagram, but if we look at the space of all such persistence diagrams with some suitable metric, some of which Peter mentioned in the morning, the Wasserstein metric, then it becomes a metric space. And the question is, does that space in some of those appropriate metrics embed in Hilbert space? So that is the question we are looking at. And when we talk about embeddings, we talk about we become increasingly or decreasingly ambitious. So we start with, are there isometric embeddings? If not, are there bilateral embeddings? Or if not, are there coarse embeddings? So that's the main question. So I'll now say a little bit about the tools from coarse geometry. So the tools used is coarse geometry, which I've been looking at the first 10 years or so. So the general theory of coarse geometry is based in terms of abstract coarse structures. We have terms like control sets and entourages, which some of the participants here are familiar with from earlier years workshop. But we will not talk about any of that today. Everything will be metric today, which is the bounded coarse structure. And our embeddings will be quasi-isometric embeddings, which are mostly familiar to people here. So there are embeddings with bounded linearly bounded distortion, let's say. And then the notion of equivalence are, there are embeddings and the functions are also coarsely onto, that means onto up to some sort of bounded, uniformly bounded bound. So these would be quasi-isometry, which are well known to geometric group theories, but we will coarsen it a little more and we will talk about coarse embeddings, which means those functions are no longer linear, they are just functions, non-decreasing functions going to infinity. So that's the setting, the metric spaces and this notion of equivalence. And then the other ingredient we use is the idea of dimension. So we look at a dual notion of dimension to topological dimension. It's called asymptotic dimension. A lot of usual participants here are familiar with it, but I will mention it in case some people are not. So we start with the usual definition of covering dimension, where open covers have refinements of bounded multiplicity, and then we dualize it. So the usual ways of dualizing to asymptotic dimension is just dualizing directly, but instead we will be looking at, for our purposes, an alternative definition of asymptotic dimension, which is we'll look at what dimension 0 would be. And I expressed it in terms of scales because it meshes well with the idea of this persistence. So let's this is a little unusual, but let's define asymptotic dimension by defining asymptotic dimension 0, fix a scale up, then define the R scale dimension to be 0 if the space sort of falls apart as a union of blobs, which are R disjoint, and the blobs are uniformly bounded. So that would be dimension 0 at scale R. And then asymptotic dimension 0 would be, for all scales R, we have R scale dimension 0. So once you define this asymptotic dimension 0, it becomes easier to define asymptotic dimension n. So there are many definitions. We are equivalent, of course. We will focus on definition 3, which is what we need. For each scale, again, it's a thing about scales. It suits us. For each scale, the space sort of decomposes into n+1 parts, and the R scale dimension of each part is 0. So that's the definition we will focus on for asymptotic dimension. And with this notion, for those who haven't seen it, there is exercise to, one direction of this should be an exercise that checking for yourself by drawing pictures that asymptotic dimension of the plane is less than equal to 2. Showing it is exactly 2 is a little more difficult. We'll come back to this later. Coarsely equivalent metric spaces, according to the coarse equivalence notion we talked about earlier, have the same asymptotic dimension. I'll just mention only the properties of asymptotic dimension that we'll be using in this talk, and they are finite unions. So if you know the asymptotic dimension of pieces, you can estimate the asymptotic dimension of finite unions and the asymptotic dimension of products. More or less, there are parallels of this in, of course, in covering dimension theory. And then there are some interesting things how dimension behaves under mappings. I'll come to that towards the end when we use it. And finally, in this short review of coarse geometry, is what our interest is. It's a known result that spaces of finite asymptotic dimension coarsely embeds in Hilbert space. And the way of looking at this is by defining asymptotic dimension by the equivalent notion of small Lipschitz uniformly co-bounded maps to simplicial complexes. So shortly, in short, roughly speaking, the proof of this embedding result is you get these small Lipschitz maps, and then you go on taking epsilon smaller and smaller, let's say 1/2 to the k or something, and get in a sequence of those maps, and you take the direct sum of all these maps, and then you get such a coarse embedding in Hilbert space. So that's my very short review of the coarse geometric techniques we'll be using through asymptotic dimension. Coming back to the work at hand. So Peter reviewed in the morning the metrics one puts on spaces of persistence diagrams. So if you remember the way he talked about it, we have these, suppose you have two persistence diagrams, they may not be of same cardinality. So you can have a partial, you can have some subsets of equal cardinality from those persistence diagrams and have a partial and have a bijection between those subsets. So such a thing is usually in the literature called partial matching. Partial because it's a bijection between subsets. And then the last line probably shouldn't be read because it is not just looking at that. It is not very illuminating. What is happening is encoded in the next picture. Suppose you have the black or violet, whatever they are, dots, 4-dot set. That's one persistence diagram. And the green set, that's another persistence diagram. We see that they are not of the same cardinality. So we take a subset of pairs of points, and that's my partial bijection. And the other 3 points, 1 green and 2 black or 2 violet, are floating. So we match them to nearest points in the diagram. And we calculate all those distances in some metric, let's say the d infinity metric on the plane. And we find the maximum of all those distances. And then this was only one partial bijection. Then we take the infimum of them over all such possible partial bijections. And that's the metric. That's the classical way of expressing this metric. This is called the bottleneck metric. This is a different metric from the one Peter mentioned this morning. And that metric is also defined in the similar way. So this is the metric on the space of these diagrams. So we redefine it in a slightly different way. So the first contribution that we do is redefine this metric. So we look at this set of 1-point persistence diagrams, and then instead of the entire diagonal, we add 1 extra point, call it delta. So, and then extend the metric to this 1 point by this third line, which if you see, it is just the distance of a point from the diagonal. So by that, we extend the metric, and then we take a product of it and mod it by the symmetric group of n letters, so it becomes a configuration space, an unordered space. And we have natural inclusions from n to n plus 1. And then for getting the whole space, we take the union of all of them. So this is the set, and then we define the metric in this way. So we add some fake points. So the best way is to probably, instead of looking at it, is to look at this picture again. The left-hand side was my picture from the last case. And then the right-hand side is, instead of 4 points, I put 4 more positions with these diagonal points, which I call delta. And then instead of a partial, what this trick does is, instead of a partial bijection, it becomes a real bijection. Now the two diagrams are same cardinality. So I have a real bijection. So why do we do this? We do this because at the end, we want a quotient by a group. and then we will have the quotient by this symmetric group. That's why we reformulate the metric in this way. So that's so this is the Wasserstein metric he mentioned in the morning. I'll skip it. It's the same way, defined in the same way. So coming back to embeddings, first of all, a little bit of history. There are no isometric embeddings. Well, the easy reason is spaces of persistence diagrams are not uniquely geodesic, so there wouldn't be isometric embeddings in Hilbert space. More interestingly, it was shown that there are no bi-Lifshitz embeddings by Bauer and Carrier in Hilbert space. So this was already known. There are no bi-Lifshitz embeddings. So that leaves the question of coarse embeddings. Now, various people over the last few years, one group by Bell and others, and then Bubenic and Peter and Wagner, they showed that by various ways that these spaces are not of finite asymptotic dimension, which means we cannot go the quick way, because remember, if they were finite asymptotic dimension, there would be embeddings in Hilbert space by the result I mentioned towards the beginning. So that way is out. So the first result we have is a negative result, and this was shown independently by Bubenic and Wagner and Werk and myself, that the bottleneck space does not coarsely embed in Hilbert space. And it is shown by a result of Dranishnikov essentially. Dranishnikov had this example of a space which does not coarsely embed in Hilbert space, made out of sort of coarse disjoint union of Z mod n's and their products. So this is a known result, and then we showed that every finite metric space embeds isometrically in some bottleneck space. So combining these two and creating this disjoint union, one shows that the bottleneck space does not coarsely embed in Hilbert space. So that's out then. Afterwards, Wagner showed that the Wasserstein space, when P is bigger than 2, also does not coarsely embed in Hilbert space. So these are negative results. About positive results, so okay, it is easy to show that the bottleneck space and the Wasserstein space are coarsely equivalent. So the first point is we showed that the 1-point space has asymptotic dimension 2. Why is that? It is a sort of a modification of the corresponding, the 3-color proof of showing that the plane has dimension less than equal to 2. So we have this 3-colored brick decomposition of the bottleneck space on 1 point that should show that asymptotic dimension is less than equal to 2 almost, but you may think, what about this huge infinitely long brick? Isn't it of infinite size? It should be of bounded size. But the interesting point is, because of the nature of the bottleneck metric, this entire infinite looking brick has a finite size. In fact, it has size only if the small length is r, then 2r plus 2r plus r. It has only size 5r. So this because it is close to the diagonal. So that gives number 1, and number 2 comes from the fact that one can embed larger and larger squares in this space by moving the square sufficiently away from the diagonal. It is essentially like the plane, so you can embed larger and larger squares in this space. So that gives the other direction of the inequality. So, and the final tool is if I have a proper metric space and the finite group acting by isometries, then the quotient has the same asymptotic dimension as X. So I'll skip this, and that is used by us to show that the endpoint space has dimension 2n. And here is a quick slide showing the proof. We do it in 3 steps. I'll take 1 more minute. 3 steps. The first step is we fill in n spot of 2n spots by diagonal points. And essentially, so it is the endpoint space. So by the earlier result, asymptotic dimension of this is less than or equal to 2n by taking products of 1-point spaces. Step 2 is we take union of all possible such things from step 1 by moving the blank spaces to other spaces. So it's just a combinatorics problem. So we show that asymptotic dimension of that piece that union is 2n by the finite union theorem, because there are finitely many choices using combinatorics. And the third step is the result by Kaspersky, that if we mod out by a finite group, which in our case is the symmetric group of 2n letters, asymptotic dimension is preserved. So the asymptotic dimension is 2n. So that tells us that asymptotic dimension of the space on n points is 2n, and which gives us by the earlier result, classical result, that they coarsely embed in Hilbert space. So this is the result, and this is now published recently. It was submitted in 2019, but it is published in the proceedings recently. So I think I'll stop there.
Okay, let's all thank Atish one way or the other. Does anybody have any questions?
I'd like to ask a question, Atish.
Yeah.
So it all went by quite quickly, but I just want to clarify. So the result of Daniel Kaspersky is for proper metric spaces, right?
Yeah.
But space of Hilbert space, space of persistence diagrams need not be proper, or how do I have it wrong?
Actually, we use the part of, there are 2 points in it. First of all, is it not proper?
If one takes a sequence of points at the same distance from the diagonal, then I suppose they are all within some bounded distance of one another.
Okay. And the second point is, that the part of the result we use that doesn't need properties. So we mention it in the paper. Part of Kaspersky we use that does not use properties. But you were right. Yeah.
Essentially, it has to do with coarsely n-to-1 maps, right?
Exactly. It has to do with coarsely n-to-1 maps. Right? It has to do with one of the embedding, one of the dimension lowering theorems. Yeah.
Thanks. That makes sense.
Any other questions? Okay. Well, if not, let's thank Atish again.
Wait, Greg, can I interrupt?
Yeah, go ahead, Rick.
Yeah, I couldn't unmute, but I had a really naive question, which is, you were talking about things that embed in Hilbert space coarsely. If you have something of, what's the term, coarse dimension n, does it embed coarsely in some finite dimensional space? 2n plus 1.
Actually not. I think we actually not. No. It embeds in Hilbert space. No, I don't think so.
Okay.
Yeah. Because the thing is, we have the proof goes by taking a product of infinitely many single embeddings. Yeah. As far as I know, yeah.
Okay. Any other questions? All right. If not, let's thank Atish.